So we're going to continue this example that we were doing before, where we're trying to maximize a multivariate function subject to some constraint. So the example we thought about is if this is a profit function, we're producing good x and good y, and we want to make the most money possible and know how much we should produce, but we have only a limited capacity of machines that can produce good x and good y. And so we did this quickly in Solver. We just maximize this function and set a constraint of x plus 3y is less than or equal to 69, and we get our answer quite easily. The question is, what is Solver doing behind the scenes? And what Solver is doing is what's called a Lagrange. All right, and so we're going to rewrite our constraint slightly different. We're going to say that x plus 3y is equal to 69. Now the reason we do that is because we know the function is concave. And so if we're right here on the function, if we produce a little bit more x, we'll be right here, and we'll make more money. If we produce a little bit more y, we'll be right here, and we'll make even more money. So if we're ever below the constraint, if we're ever at 68, then all we need to do is produce one more x, and we'll make more profits, and then we'll satisfy 69. So that's why we can rewrite the constraint as a binding constraint, meaning that we're going to be exactly at 69. So I can then rewrite this as 69 minus x minus 3y is equal to 0. So now this term right here is equal to 0. And so what Lagrange does is we write a cursive L for Lagrange, and Lagrange is going to equal f of xy plus lambda, a Greek letter L, lambda, which is called the Lagrange Multiplier, and just multiply that by the constraint. And the reason this works is our constraint is equal to 0. So the Lagrange is equal to the original function plus a number, lambda, times 0. So it's just equal to f sub xy. And that's really not bad at all. But when we take our first order conditions to try to optimize this function, it's going to take into account the fact that our constraint has an x, and so we'll then have to deal with that. So our Lagrange in this case is 120x minus 4x squared plus 2xy minus 3y squared plus 96y minus 102, that's f of x, y, plus lambda times 69 minus x minus 3y. And so this is now our Lagrange equation. Well, to optimize this, we just need to take first order conditions. So we take the partial of the Lagrange with respect to x. So here we get 120 minus 8x plus 2y. There's no x's here, but you'll notice that this lambda is multiplied by x here, so it's minus lambda equals 0. If we do our partial with respect to y, we'll get 2x minus 6y plus 96. Here we have lambda minus 3y, so it'll be minus 3 lambda is equal to 0. And lastly, we take the partial derivative with respect to lambda, which is just equal to 69 minus x minus 3y is equal to 0. Now if we were to compare this to what we did beforehand, when there was no constraint. So here is the same function that we did earlier, and we optimize this function, so we get 120 minus 8x plus 2y. And this is how we optimize that function with no constraint. What you'll notice here is that when we did this with a constraint, so we can get these in the same shot, is the first order conditions look very similar. 120 minus 8x plus 2y. That's exactly what we had over here with the unconstrained. The only difference is now we've incorporated lambda. Same with this partial derivative with respect to y. We've incorporated a lambda compared to what we did before. And lastly, the third constraint is just simply the constraint that we had of x plus 3y. And so we get this, and this is just a system of equations where we have 3 unknowns and 3 equations. All right, so we can do this by hand. Trust me, it's very unfun. If you ever have Dr. Baker as a teacher, he loves doing these. So you should always ask him in every class, could you do a Lagrange for me by hand on the board? And he would love to do it for you. Or we can put this into Excel and let Solver do this for us. But what we did, rather than take this first derivative and then put that into Solver, is what we did last time is we just maximized this equation with our constraint as added in. And what Excel is doing, what Solver is doing, is exactly this behind the scenes. So it's not important that you know how to do this, but it's important for you to realize that this is what Excel is doing. And the reason why it's important is because Lambda, or Lagrange multiplier, has a very important interpretation. Lambda is called a shadow price. And what that means is, let's look at our example here, is our machines can produce only 69 units. Well, the question is, what if we were to make this number, let's change colors a little bit to show that we're changing things. What if we were to make the constraint 6 plus 3y is less than or equal to 70? If we were to change our constraint by just a little, what would happen to our profits? Well, from this equation here, the way we'd answer that question is what you're asking is, what's the partial derivative of lambda if our constraint changes by just a little? Well, if that's the case, from this equation here, think of this as y equals mx plus b. That is just equal to lambda. And so what lambda tells you is how your objective function, in this case profit function, changes with a change in the constraint, such that if I can increase my machine's capacity to 70 instead of 69, how much will my profits increase? And we'll look at examples where we actually solve out for lambda. Now by hand, this is how we'd solve it out. But with Solver, we just click one button and it will tell us what the Lagrange multiplier is. So this is our Lagrange multiplier. And so this is the Lagrange setup. And we'll look at some examples, but this is exactly what Excel is doing behind the scenes when we simply maximize our objective function with a single constraint.